Okay, so to explain the unconstrained versus constrained ordination. So for an unconstrained ordination, I'm going to give you an example of a sea surface temperature time series. So it has a temporal component. Every year we take a measurement. It has a longitudinal component and a latitude component. So we have an X matrix of M times N, where M represents spatial location and N represents time. So we have N data points in an M-dimensional space. And if I run the PCA on that, I'm going to get, instead of just time series versus time, I'm going to get the relations, other principal components that are hidden from me in the original matrix. So I have a new matrix now, which is composed of PC1 and PC2. And what I can see here are the PCA weights. And I see basically the pattern of global warming in PC1. So if I plot PC1 over time, what I'm seeing is basically global warming. And PC2 explains the rest of the variance. And you can see here it's really across the equatorial and tropical Pacific. We're talking about the ENSO cycle is seen as principal component 2. Constrained ordination is what we're going to look at next, where we have the extraction of information from the data set, and we're extracting information that can be explained by external variables. So for example, how the species of iris is affecting how we can tell them apart using PC1 and PC2. So we're going to start by running a practice run of this, and then we can, while we interpret the data, we'll pay particular attention to what the eigenvectors are, the eigenvalues, the loadings, things like that. But when it comes within the data analysis, it's actually easier to understand than just using linear algebra. So the first thing you're going to do is order your data in an M times N matrix. Okay, so you want all your variables one next to each other, like we saw earlier, and down the rows you're going to have your different samples. Like with other statistical analyses, because this is a correlation matrix, we're looking for normality, and we're going to center and scale the descriptors, right? That was our first step. So we're going to center and scale. You'll see that this is all happening in one line of code. But and now we're going to find a PCA. You're going to use a PCA to find the direction of the highest variance in your data. And we're going to determine the number of important principal components, because we're going to have as many principal components as the M dimensions of my matrix. But I want to know how informative, my whole point is to reduce the variability. I'm sorry for the background noise. Reduce the variability, but we have really trying to put it into a two-dimensional space sometimes. So I want to know how informative the first two principal components are, the first one and then the second one. And then I have my principal components, but really what is principal component 1? I want to bring it back to real life, and I want to know how the different original descriptors, my original measurements, what their loadings are onto these principal components that I've designed. And then, of course, I want to visualize and interpret this analysis. So, say, for example, I'm looking for something that sets these lakes apart. I want to look at things that characterize each lake. I want to use something that allows me to detect differences amongst lakes. So what can I measure? So you can take a lot of different measurements, and if you can, measure them all. If you want to measure the pH, the temperature, the amount of dissolved oxygen, some of these are going to co-vary, right? But I mean, it doesn't matter, because my principal component analysis is actually going to reduce the redundancy in my data set and create new principal components, new axes that are getting rid of this covariance, right? That's how we diagonalized the matrix, the covariance matrix. So I can have lake 1, lake 2, lake 3, and it has different pHs, different salinity, temperature, oxygen. Okay, so here's my M. So I actually have 4 measurements, not 5. Okay, it's not because this is just the name of the lakes. And then I have in a time series, or in my case, just samples. Okay, so I just made up this data. Please don't use it to look at different lakes. I don't even know if these are reasonable numbers. And so first of all, I'm going to run a covariance analysis. So I'm going to plot basically these pairs. Remember, so pH against itself, salinity against itself. Here are my diagonals and off diagonals, and these are the relations between the two. I can already see that temperature and oxygen, they go hand in hand, right? Because usually the amount of oxygen, remember, that Henry's law, the amount of oxygen dissolved in the water is dependent on the temperature of the water. So we have a really strong relationship between these two. So if I had a look at this in terms of the Pearson's R, then I can see a really strong negative correlation in this one. And remember, it's symmetrical, so I have the line of diagonals, and the off diagonals are symmetrical because temperature and oxygen are linked in the same way as oxygen and temperature. There's no direction. And then I run the principal component analysis, and I very quickly get something that looks like this, but we're going to run it together. But this is the output of different measurements. So the first 10 were lake 1, the second 10 were lake 2. So these are all different lakes, and how they distributed across principal component 1 and principal component 2. What you can see here are the eigenvectors. You can see what originally oxygen used to do, originally what pH used to do, originally what salinity used to do. So we can see that PC2 is really composed of a lot of pH, and PC1 is composed of oxygen and temperature in opposing directions. And those opposing directions make sense to us because they were very correlated, just negatively correlated. One's pushing this way, the other's pushing that way. So I'm not interpreting this yet. I'm just showing you what, just to try to put this into context, okay? So there's some sort of rotation on, so I've taken my data, which had oxygen and temperature, rotated it a bit to get PC1. And then I'm trying to look at whether my lakes are different, and they are different along PC1. I can see that all my lakes, all these numbers from here, the low numbers are lake 1, and I have lake 3 over there. We call it clustering along the PC1 axis. PC2 isn't really helping me define clusters, but I can see lake 1, 2, and 3, and they really differ along that oxygen and temperature axis, which are quite redundant, right? I mean, like, I don't need both of them. Anyway, I'm not looking at them anymore. I'm looking how they change along PC1, and how much temperature sits in PC1 and how much oxygen sits in PC1 is really the loading, and we're going to have a look at those numbers in a minute.